Today we will see the arithmetic operation in various number systems. First we will see the arithmetic operations in binary system. Let us study the binary additions. Here figure 1 shows a truth table for addition of two binary bits. There are 4 rules. Since there are 2 bits in the addition, there are 4 combinations exist. For example, number A and number B are the binary numbers. When both the bits are 0, the binary sum will be 0 and carry will be 0. When bit A is 0 and B is 1, then sum is 1, carry is 0. When A is 1 and B is 0, the sum is 1 and carry will be 0. When both the bits are 1, that is 1 plus 1 is 0, that is the sum, and carry is 1. Means when 2 bits are 1 plus 1, then sum will be 2 bits. So 2 single bit addition, when overflows, it generates 2 bit sum. One is the carry bit and another is the sum bit. When multi-bit binary addition is to be done, then it is similar to our conventional multi-digit decimal number addition. We will add the bits of the two binary numbers column by column. Let us take the example. Suppose there are two numbers A and B with the bit number B0 to B4. Then the binary addition can be done column by column. Say for example, bit 0, B0 here is the bit 0 of number A is 1 and bit 0 of number B is 1. So 1 plus 1 is 0. That results to sum 0 and carry 1 here. In the second column, this carry is 1 plus number A is 1. So 1 plus 1 plus 0 is 0 plus carry 1 again. Again in the third column, 1 plus 1, 0 plus carry 1. In the third column, this carry plus the third bit of number B, that is 1 plus 1, is 0 again and carry 1. Now in the fourth column, you will see that both number A and B have bits B4 as 1. So 1 plus 1 plus carry 1 is 1, 1. So sum is 1 and carry is 1. So 5-bit number is now getting the summation as 6 bit. Out of that, lower 5 bits are the sum bits and the last MSB is a carry bit. Now binary subtraction. Again we will see the rules of subtraction. Here the table shows the rules of single bit binary subtraction. Number A and number B are the single bit binary number. When both the bits are 0, 0 minus 0, subtraction is 0 and borrow 0. 1 minus 0, subtraction is 1 and borrow 0. 1 minus 1, subtraction is 0 and borrow 0. 0 minus 1, the borrow is 1 and the subtraction is 1. When multi-bit subtraction is to be done, it is again done similar to the multi-bit addition. Here only we apply the rule of subtraction and we do the subtraction column by column. So number A and number B are shown here. B0 to B4 are the bits of the number. In B0 column, 1 minus 0 is 1. In B1 column, 1 minus 1, the borrow is 0 and subtraction is 0. In B2 column, 0 minus 1 is give you the borrow 1 and subtraction 1. This is the last combination shown in the table here. In a B3 column, here you will get 1 minus 0 minus 1 is 0, subtraction is 0 and borrow is 0. In B4 column, 1 minus 1 is 0 and therefore the number A 11011 minus number B 10110 gives rise to the subtraction 101. No borrow is generated, so number is positive and number A is greater than B. You can make the practice of adding multi-bit binary number with the following exercises. It is left to you as home exercises. Some of the questions those are asked in the examination are now considered. Add and subtract decimal number 26 and decimal number 32 after converting them to the binary numbers. Means there are addition of the two numbers and then you have to perform the subtraction of the two numbers, and that is to be done by converting them to the binary number. Here in step 1, both the decimal numbers are converted to the binary number by the double system we have already seen. When any number, decimal number is to be converted to binary, it will be successively divided by 2 and the quotient will be successively divided by 2 and the remainder will be noted in each step, and the process will be continued till the quotient becomes 0. Once the division process stops, then the last MSB, remainder will be the MSB and the first remainder will be LSB. So in short, we can say go on dividing the number by 2, note down the remainder. When the process ends, write the number from bottom to top as MSB to LSB. So we will convert, we have convert here 26 to number 11010 binary, and we have converted number 32 decimal by successive division by 2 to a binary number 100000. Now both the numbers we got. So in second step, we will perform addition of the two numbers. So we will write the number column by column and add the number. 0 plus 0 is 0, 1 plus 0 is 1 here, 0 plus 0 is 0, 1 plus 0 is 1 again, 1 plus 0 is 1 again, and 0 plus 1 is 1. So sum is 110010. If you convert this binary number to decimal again, you will get the number 58 decimal, and which is also verified as 26 plus 32 in decimal is 58. Now perform the subtraction. In the subtraction, we take again the two numbers, 32 as number 1 and 26 as number 2. And we will subtract the two numbers column by column, and we get here bit by bit subtraction, and the result will be 000110. Right. Here the 32 minus 26 is 6. Here it is wrongly printed at minus 6. Therefore, here also you will get the result, binary result 110. 110 corresponds to decimal number 6. We will make the correction, this typo correction in this problem. The minus sign will be not there. If you do the reverse procedure, 26 minus 32, then the result again same, and you will get the borrow generated here, and that indicates that the number is negative. The next operation, arithmetic operation, is binary multiplication. The rules of the multiplication in binary are very simple. For example, if two bits are to be multiplied, say bit 1 and bit 2, say A and B, since 0 into 0 is 0, 0 into 1 is 0, 1 into 0 is 0, and 1 into 1 is 1. Means anything multiplied by 0 is 0 and 1 multiplied by 1 is 1. When you want to perform multi-bit multiplication, the procedure is very similar to decimal multiplication, but it is very easy in binary, because in binary there are only two state values, logic 0 and logic 1 for the bits. This algorithm of multiplication is also called as shift and add algorithm, to which we are very familiar in decimal number system. Now let us see how to apply this generalized algorithm to binary multiplication. Suppose first number is A0 to A3. Say A0, A1, A2 and A3 are the 4 bits of number A. That is to be multiplied by the multiplicand number B, that is B0, B1, B2, B3. So what we do normally in the multiplication, we will multiply bit by bit. So first we will take a bit B0 and multiply number A, that is A0, A1, A2, A3 by bit B0. So therefore, when B0 multiplies A0, it is A0 B0, then B0 into A1, A1 B0, then B0 into A2, A2 B0, then A3 B0. So that is the first term you are getting, right? Then we will multiply the number A by using number B1. But this number B1 is at the second position from left. We will shift the partial sum by one position. So here we will shift the partial sum by one position and then multiply number A with B1, and we have written it here, right? So similarly, in the third step, we take number B2 and then B2 multiplies all these 4 bits. Since B2 is in the third position from left, we will shift the partial result by 2 positions and write the multiplication that is generated by B2. Then last bit B3, we will multiply the number A again by B3. Now this bit is at the 4th position from left, so we will shift the partial product by 3 positions and then write the partial product. After writing the partial product, we will column by column add this partial product, and the result will be obtained, and that is the multiplication of the two numbers. Let us take a real example. Multiply 9, that is binary 1001, by decimal 8, that is 1000. So number A is 1001 and number B is 1000, shown here. 1001 is multiplicand and 100 is a multiplier. Now consider the B0 bit of the multiplier. So this 0. 0 is multiplied by 1001. The partial product is 0. So we have written the partial product 0, 0, 0, 0. Now we will take the bit B1, that is also 0. We will shift the partial product, and the partial product 1001 into 0 is 0. Again we will add this partial product by shifting it left by one position. Bit B2, that is also 0, therefore partial product is 0. We will shift it by 2 position and then add. The bit B3, which is 1, and that is again multiplying 1001. The partial product is 1001. Again it will be shifted left by 3 position and added. Then column by column we will perform the addition of all these partial products, and we get the final answer 1001, 000. That is the multiplication of the two binary numbers shown here. And this number is corresponds to decimal 32. That is, binary equivalent of decimal 32 is 1001000. The binary multiplication of the fraction can be performed on similar tracks. Initially we will not consider the binary point. We will do the multiplication bit by bit to the total bits in the number A by number B. Every time we will shift the partial product by one position. We will generate the column by column addition, and then we will put the decimal point. Since here the decimal point in number A is after 2 positions and in B the decimal point is after 2 positions. So total number of positions the decimal point will be shifted left in the result are 2 plus 2, that is 4. So therefore we will put a decimal point after 4th position. If you consider as 0 base position, then this is B0, B1, B2 and B3. After B3 we will put here the decimal point, and therefore the result will be 101001.1011. The same procedure we are following for the decimal multiplication. Here, since the binary number have only 2 states, the product will be either the number itself or 0, that can be a partial product. So therefore the multiplication is very simple. The next arithmetic operation is binary division. It is also called long division method, and it is also similar to the decimal division we are following. Let us consider the number. The dividend is 110 and the divisor is 10. So binary number 110 will be divided by the binary number 10. So write it like this. Here the dividend is written 110 and divisor 10 is written. Now take a quotient of 1. 10 will be 10 will be subtracted from 1. Column by column we will subtract. 1 minus 0 is 1. 1 minus 1 is 0, and therefore the remainder will be 1. Then next take the next digit on this subtracted result subtraction. Then the number becomes 10 now. Now divisor is again 10. It will give the quotient of 1 again. So 10 into 1 is 10. 10 minus 10 is 00. And therefore you are getting the quotient of 11, that is corresponds to decimal 3. 10 corresponds to decimal 2 and 110 corresponds to decimal 6. and therefore if you check in the decimal division, 6 by 2 is 3, and here the binary division also shows the same thing. Here somewhat more number of bits are considered. Here divisor is 101, so we will consider first 3 bits. 110 divided by 101. The quotient will be 1. We will subtract 101 from 110. The remainder will be here 1. We will take 1 on it. Then the sub remainder will be 0011. Divisor is higher, so quotient will be 0. Again, we will take the next bit down. So we will get the sub remainder as 111. Now divisor is less than this number. We will have a quotient of 1. We will subtract from 111 101. We will get the subtraction as 010. Then we will take the last digit of the binary number on this remainder. So remainder will be 100. Since this 100 is less than the divisor, the quotient will be 0 and remainder will be 100. And therefore you will have a quotient, final quotient as 1010, divisor 101 and remainder 100. 100 corresponds to 4. 1010 is 10 and 101 corresponds to 5. So 5 into 10, 50 plus 4. 110 is corresponds to 54 decimal. So one thing to be noted here that when you perform the integer division, then decimal point position will be decided by the position of the decimal point in the dividend. Whereas division of decimal by integer, then decimal point position will be decided by the position of the decimal point in dividend. When the division of decimal by decimal, then convert the divisor to integer. Means always the divisor is made integer by shifting the decimal point to right in both numerator and denominator, and then perform the long division and use the case 2 to decide the decimal point of the division. These rules are exactly same as the rules of decimal additions. So that's all about the arithmetic operation with binary numbers. The types of numbers in any number systems have following characteristics. The system may be decimal system, binary system, octal system or hex system. The first category of numbers are terminating decimal numbers. Means they can have the fixed number of digits like 34.9807. After that the digits are 0. 55.5 or 55.5000 means the value will be fixed and there is no digit in continuation. Non-terminating decimal number. These numbers are indefinite numbers and they will be continued at infinite number of decimal places like 25.214212 dash dash dash. It will be continued like the value of root 2 or like the value of pi. The number generated is continued up to infinity. These are called non-terminating decimal number. Recurring decimal number. The numbers in which the number combinations are repeated indefinitely called recurring decimal numbers, and non-recurring decimal numbers in which the numbers are continuously present up to infinity in the fractional portion, but they are non-terminating. The number representation used in the binary system are of two types: signed numbers and sign magnitude numbers. The signed numbers have sign. In decimal number, signed decimal number, normally we are using plus and minus sign to indicate the positive and negative decimal number. Whereas in digital circuit there are only two symbols, 0 and 1. There is no plus and minus sign. Therefore, in digital electronics, normally for plus and minus indication, one MSB is attached to the number, and that MSB bit is indicating the sign. Normally, bit, if it is 0, then it is considered as a positive number, and if this MSB is 1, the convention is it is a negative number. Whereas this is a convention. This convention, once accepted, we have to follow it throughout the circuit and take care of sign representation of the convention. Otherwise, electronic circuit doesn't understand a bit and sign. Sign magnitude representation is another form of representing the number. So in sign magnitude number, as we discussed, one bit is reserved for the sign and remaining lower significant bits are used for magnitude. The MSB is reserved for sign and remaining bits are representing the magnitude. Let us see the example. Here it is a 8-bit number. Out of that, MSB is reserved for sign in sign magnitude number, and remaining 7 bits indicate the magnitude. When the sign bit is 1, the number is treated as negative number, means that magnitude is considered as a negative magnitude, and when sign bit is 0, the number in the magnitude is treated as positive number. Here the typical number is 0000100, that is corresponds to 4. But sign bit is 0, means it is minus 4. And in the second representation, same magnitude is with 0 sign bit indicates the number is plus 4. So here another example you will see. The 8-bit number shown here. Total number of bits are 9